Okay, good morning. So I think we still have to, survive with the missing of the panel. So still using the laptop. I hope, they can next time the lecture, everything will be fixed. Okay. Maybe the resolution may not be as high as you like. So if you have a laptop, you do not like to view this one in a low resolution mode, you just can, in the meantime, you can just watch your own laptop. Maybe it could be better. Last time we discussed quite a few classification methods we call advanced classification methods, including Bayesian belief networks, neural networks, support vector machines, and pattern-based classification. Now we get into some other, not a very, very dominant, but still quite popularly used classification method. One method we introduced called lazy learners or k-nearest neighbors. The general philosophy of lazy learning is you probably do not want to construct a model once data came. Okay. That means the data may give you lots of training data. You probably just organize in some way. For example, build some kind of indexing, doing some kind of organization, but you do not really try to build a model. Okay. That means you are lazy. Before people are asking you, so you never, do any real thing on model construction. But when people give you a testing data, real data, ask you to give the labor, okay, that's a time you want to work hard. And how do you work hard? A popular method called k-nearest neighbor means you try to ask your nearest neighbor. Okay, that means sometimes suppose you have 5 neighbors very close to you. You ask these 5 neighbors, say, since the people give you this testing set, it is so close to you, what is your vote? Okay, basically, that's the general philosophy. That's about lazy learning. Okay. Lazy learning, there are several lazy learning methods. People call this one is instance-based learning because people give you instance. And that's the case. You are busy, you try to look at other surrounding instances. Okay. So I'm just wondering, is here not very stable? Seems to be. Hopefully this time it will be okay. Maybe this, sometimes the Mac is here have problems on the connections. Hopefully it will come back in a minute. What's the problem? Yeah, I think they really need to fix it quicker. I do not know why it takes so long to fix it. And I hope we don't have to reboot again. What is the real problem? Let's see. Let's see whether we can. I'll see whether the small one will work. Yeah, the small one is working. Okay, so it comes back magically. So let's just survive with this environment. Okay, so we got several methods. We say the instance-based learning. We are going to introduce essentially two. One is very popular one called k-nearest neighbor approach, because another one called locally weighted regression. The general philosophy for locally weighted regression, I'm not going to introduce the detail, is you basically try to do the nearest by you want to construct the regression model. Okay, then you probably try the average regression or something. You can find some numerical values. Okay. But we're going to introduce k-nearest neighbor approach and a case-based reasoning approach. Okay. The k-nearest neighbor, the general philosophy is, okay, when you get your training data, which usually is in the n-dimensional space, you get training data, you sort of indexing them, put them in the right place. Okay. And you do not do any model construction. When the query comes, when the instance comes, say, what is the labor? Okay. Then what you need to do is you try to, based on your instance space, that means based on your training data, different dimensions, they have a distance. You base on the training dimension, different dimension space, you try to find your nearest neighbor. Okay. Nearest neighbor means who are closer to me, okay, in the n-dimensional space. And once you find the nearest neighbor, they give you the labors, okay, give you the labor or give you the weights or confidence of their classification. Okay. And based on this, you try to integrate them. Maybe you can do ensemble. Okay, ensemble means what is the majority vote? And then you are going to give the labor. And to do this, usually people try to do a little pre-processing to help you to find what is your nearest neighbor. Okay. To do this little processing, actually there's one quite well-known diagram called Von-Neury diagram. Von-Neury diagram essentially is you try to compute between these 2 points. So you try to compute how to compute the nearest neighbor is you take these 2 points, you find a cutoff line right in the middle. Okay, usually you call these is perpendicular cutoff right in the middle. It comes back down again. Let me try. Okay, so that could be the laptop now this time. Okay, the laptop sometimes goes down dark. Okay. Then you try to find the perpendicular line right in the middle to separate any 2 points. Once you do this separation, you get a Von-Neury diagram. The Von-Neury diagram basically says if you fall into the space, which is not within any perpendicular line, it's just within the same, quadrant, that one, the nearest neighbor is that's a one nearest neighbor. That labor could be your labor. Okay, so that's Von-Neury diagram. But in reality, most predictions are the real value prediction in the sense you try to know sometimes the confidence or sometimes the values. What you do is you get a nearest neighbor, you do weighted distance. So-called weighted means you can see that formula here. Okay. The formula here basically says this Q is your query, the query point. This I is your instance. Okay. You get a K nearest neighbor, you get a K instances. Okay. Then this D is the distance. That means if my query point is very close to my first neighbor, okay, that one will weight somewhat more. Okay. But when they are a little far away, they will weight less. Okay. You get a different weights. You can. That means that the bigger distance, the weight less. That's why you can see it's a inverse. Okay. It's 1 over the distance. Actually, you try to make sure it's not a positive or negative distance. You can square them. So in that sense, the bigger distance, the weight's less. The closer to your query, the weight's more. Okay. So that's basically the distance based. Of course, you may say, what about distance 0? Okay. Distance 0 means it's a right match my training instance, exactly the same as training instance. In that sense, you can think the weight is infinity means you already got the label. Okay, that means if you get a tissue, the tissue already, the doctor already said this one has cancer. Then you get the exact tissue, put it in. You say what it is. Then the doctor will still say that's a cancer. Right? So the weights become infinity because it's exactly the same. Is that clear? Okay. So that's the first advantage is this one is pretty robust in the sense because you have k-nearest neighbor. Even you are lazy, usually the labor, you get enough labor, closest labor, they give you something you can trust. Okay. So that means even sometimes the model is lazy, but because it's so close to your neighborhood, so close to your region, sometimes the quality is not bad. Why? Because you think about the global, like a decision tree. They think about all the global things. Okay. They try to partition space, all based on the global decision. But global sometimes does not really match so well with your local. Okay. So sometimes you are lazy, you're not too bad, because you have enough neighbors give you consistent, for example, voting. You will be very confident you must be right, because it's closest neighbor, right? But that one has one problem, is curse of dimensionality. Curse dimensionality means once you get a very high dimension, you get like we usually take a picture like 2D. The 2D, 2-dimension, you try to find nearest neighbor. It's quite trustable. Okay. But then, if you get many more dimensions, actually try to calculate the distance. Sometimes it's not very effective because suppose you get 20 dimensions. Okay. Which dimension weighs more? And their distance could be just the dimension distance rather than real distance. Okay. To that extent, once you get a very high dimension, the k-nearest neighbor may not work well. So usually it works well for a small number of dimensions. Another instance-based method called case-based reasoning. Case-based reasoning actually is you construct your solution space into multiple cases, into layers of the cases. Actually, nowadays, you probably get a case-based reasoning quite well if you dial a phone. Nowadays, not so many people really, you get a real people answer your phone. Okay. What they do is you say, check your case. For example, you got something wrong, like your TV doesn't work. You call the company who produced this TV. Okay. What they say is your TV has lights on? You say yes. Okay. Then you will say whether the sound is okay or whether something is okay. They give you several things. Finally, you retrieve down into the place. They give you some kind of solution. Okay. Of course, in the real case, finally you have nothing you can answer. You just wait there. You probably get somebody come appear to get a real person to answer your case. The case-based reasoning basically, you organize all the different cases like a tree of search. Okay. That means you first check the first case. If that case matches A or B or C, then you go down to the right path. Okay. Then you check another case. So that case-based reasoning essentially is structure your problem solution into multiple cases. Then you go down, you may get the right class label. Or that means you may get the right solution. Okay. So that's the typical case-based reasoning. What they do is they sort of doing multi-layered indexing. That's exactly your telephone, right? You may say, oh, the telephone at this layer, you may have 4 cases. The other layer, you may have 5 or 3 cases. You keep walking down through the detailed cases. So that's exactly what case-based reasoning is doing. Okay, you basically try to match each thing. Okay, then you finally find the solution. Okay. And but the major challenge is usually there are lots of things that numerical are vague. Okay, you try to find whether this what they said the case is the exact match or closest match, or which one matches closer. Okay, so that's find a good similarity metric could be a challenge. Okay. Another thing is how to index them. How do you make a good judgment to go to the right tree? Okay. So those are the case-based reasoning. It has been used very popularly in classification as well. Okay. This is, in most cases, for non-numerical data, you use case-based reasoning more. For numerical data, you use k-nearest neighbor, because it's easy to compute neighbors. Okay. So this is about lazy learning. That means some people call this instance-based learning. Instance means they organize your training data into multiple instances into the right space. So that's another popular method. Then we have several other methods I'm going to introduce you. One is genetic algorithm. I think people nowadays, you hear like a bioinformatics, they discuss about genes, genotypes, phenotypes all the time, right? I think you know what is gene, how the evolution goes. Okay. This algorithm is somehow thinking something closer to the biology. Okay. Closer to the biology means they think the whole biology is to start from very simple one with the different training. They try to change their genotype, try to change their genes, try to fit the environment. Okay, then they can grow, they can evolve. So this genetic algorithm has a similar design or nature. Okay. For example, if you're just thinking about you have only 2 bits or 1 bit. Okay. So you may actually say, we probably can think about something like this. We give you this one is like a A1, A2, and then C, that case. You have 3 cases. Okay. 3 bits. 1 bit is for A1. 1 bit is for A2. The 3rd bit is for your class label C. Okay. So then, suppose you have the case is A1 is on. That means A1, the 1st bit is turned on. Okay. A2 is off. That means the first A2 is 0. Okay. Then your C2, your class C2, C1, C2, suppose you have the 2 class label. C1 means this class bit is on. C2 means the class bit is off. Okay. Then you can write your rule as 1, 0, 0. 1 means A1 is on. Okay. 0 means A2 is off. Okay. And 0 means C2 is on, C1 is off. Okay. Suppose you get this. Then you can write down like this. You say that's a rule, basically based on the training. Okay. Of course, in the real life, your genetic algorithm, your bit is pretty long. You may have many more bits. Okay. Then in different cases, you turn on and off. At the very beginning, you can assume everything is just random. Okay. But when you get a training data, you start turning this one on and off in the case. And another one comes, you will change the one. Of course, they do not have a clear statistic memory, say how many times you turn on and off. But if you have long bits, they keep training you. You keep turning on and off for many different things. Finally, you may get a rule which actually can match majority of the cases. Okay. So that's basically, they call this one genetic algorithm. That means you got initially do not assume anything. You just give the bits to the outsider. Okay. Then the training example comes. They keep changing your bits on and off many rounds. Okay. Finally, when the training is finished, it will have some kind of a classification power or prediction power. So that's the genetic algorithm. This algorithm, in the past, people evaluated this method, said, it may work for some cases, but on the other hand, the general statistic method may work even more robust. Okay. But there are recent years, there are some revival of this method. It means for some tasks, they found that this genetic algorithm actually can do reasonably well. But definite training will take a longer time, and some statistical information may not be adopted so well. Actually, for this genetic algorithm, one leader actually was from UIC. I think he was not a professor in computer science, but he was a professor in industrial, or we call general engineering in this college, called David Goldberg. If you go down to the Google, you search his name, you'll find his books and his majority of the genetic algorithms. Many researchers were his students, graduates from UIC. Okay. Once I actually attended their workshop, I found that probably over half of those professors are his previous students. Okay. So that's a genetic algorithm, but he already retired. But if you search Google Scholar, you probably find his citation probably among genetic algorithms, his citation probably still the highest. Okay. So that's a genetic algorithm. But I will not give you a very detailed introduction. Basically, that's general philosophy. Okay. You go down there, still lots of tricks. Okay. I talked to him a few times. He says, people just had a very shallow understanding of his genetic algorithm. That's why some people blame it did not work. But you go down there are lots of tricks. If you play right, it will work well. Okay. I think maybe it is quite right. Most people probably did not get very deep into his genetic algorithm. Okay. So that's genetic algorithm. Another group of people actually study another classification algorithm called rough sets. Okay. Rough sets actually was more or less proposed by a Polish mathematician. Okay. He actually worked out this. There are lots of people when I was in Canada, there were quite a few people following him. Most actually are originally from Poland. Okay. Those professors, they really like his method. This method, general philosophy is this. Okay. If you look at the picture, what you can say is rough sets means you try to get a boundary which can say inside boundary is one class, outside the boundary is another class. Okay. How to work out this boundary? This boundary was a set of claims which may form those breaks. That means each break there actually was a set of conditions. Okay. With this condition, you say going higher above this condition may be one class, low above this condition is another class. Then you get multiple conditions surrounding it. You get a circle. Okay. Then the problem becomes something as certain is above or below is fine. What about right on this breaks? That means right on this boundary. Okay. Right on this boundary, you try to make the boundary as thin as possible. That means as clear as possible. Then you have less case right on the edge. Okay, then you can clearly say it's up and down. Okay. Then you can represent your whole classification model as a set of rules or set of boundaries. You can make the right decision. Okay. That boundary, they actually call this one is some kind of matrix, like a discernibility matrix. Okay. But people actually found what his boundary can get, most statistic method also can get it. Okay, this is a group of people, they really like it. It's never been very popular. Okay, so you probably know this is another approach. Then there's another group of people actually got a fuzzy sets. The fuzzy sets general philosophy is they use fuzzy logic to do this classification. What is fuzzy logic? The fuzzy logic basically say, for example, you say somebody is tall. Okay. The tall itself, this concept could be fuzzy because You think you are tall, you go down to those NBA basketball players. They are much taller than you, right? So your tall actually is a fuzzy idea. It's not absolute tall, because you go down to many other people that could be taller than you. Okay. So then you think you are tall, you get a fuzzy value, big number 0.8 or 0.7. Okay. That means your fuzziness on the tallness is just 0.7, because there are some people actually higher than you. But if you are short, you're very short, maybe your tallness is only 0.2, but shortness is 0.8. Okay. Somehow they can give you this kind of fuzzy idea. Okay. And with this fuzzy logic, they can work out a set of rules based on this fuzzy logic. They can work out a classification model. Okay. So this, actually, there were a group of people actually interested in this. I think there were a Berkeley professor, I believe he already retired, called Zadeh, Z-A-D-E-H. Okay. He actually was one of the founder of this fuzzy logic and also fuzzy set classification. Okay. I remember once I went down to one machine learning conference. They asked me to give a keynote. Actually, that one was fuzzy sets, rough sets. Okay, those people, they have a community. Actually, that's the time they invited me to Moscow. That's the only time I've been to Moscow, actually, to give a talk. But I found that the majority of people who are, really working on this, I actually do not quite know. Those are the fuzzy people, or fuzzy sets people, and the rough sets people. They form a community. They actually keep moving on the state of the art on this classification. But it's not dominant. You can see the dominant one. I already show you the Bayesian sets, work out the probability graphic models, the support vector machines, deep learning people. Those actually become more dominant in the whole classification game. Okay. But this is another one. Okay. So now I basically give you the general overview on many different classification methods. There are lots of researchers working on different methods. Of course, if you say, who are the absolute winners? Okay. Now I probably can say recently this deep learning people really got a lot of edge comparing to the others. Like in 2009 and 2011, there were two competitions on many different items. Most are the computer vision things, recognition things. And these several deep learning methods actually win the top awards. But still, there are many other methods, like many other statisticians said, there's no absolute winner for all the cases. Okay. There are still many cases other methods may play a better role, may do something better. Okay. So it's still not say everybody's game, but it's still many people's game. Now we get into another issue is when you do classification in the past, we only say two classes, or yes or no, or cancerous or benign, or something, two classes. But in reality, you may quite often get into multi-class classification. What is multi-class classification? Means instead of you predict only one label, yes or no, or the two cases, that means we say this binary classification, you actually may predict many cases. Okay. Just give you an example. Suppose you do web page classification. The web page may say this one is some company's homepage, but the other one could be product page. The other one could be some, like a customer question answering page. So even for one company, there are lots of different kinds of pages. You try to make a prediction, you may have 5 or 10 different classes for you to make a judgment. Right? That's very popular. Actually, I remember in around 2005 in KDD conference, I met one Microsoft the ads, they call ad center manager. Okay. She actually approached me, said, you do data mining, you do classification. We have a big problem whether we can solve. I said, what problem? She said multi-class classification. I said, oh, there are lots of methods on multi-class classification. But she actually told me those methods all didn't work. I said, why didn't work for their application? They said, Ad Center, the major thing is put ads on every page. But how many ads, different kinds of ads you can put in? There are thousands of them, or more than thousands of them, like tens of thousands of them. When people traverse this web page, you want to put a proper pages down there. There are thousands of choices. Which one is right? You put it in. And that means instead of using a multi-class classification, this K is 5 or 10. They actually have tens of thousands. Okay. So which one you put in? Who can solve it? So that actually is a multi-class classification. Of course, you probably know Google, if you go down to search, you see they do have quite a bunch of ads. Those ads, actually, they use a very different methods. Something similar to classification, but definitely not exactly as we introduced here. It's much more complicated. So we introduce here, I'm going to introduce two major methods, one called one versus all, the other one called all versus all. Or some people actually call this as one versus one. Okay. If you go down to Wiki, go down to different tutorials, you see all versus all, one versus one. Looks very different. Actually, they are very similar. Okay. Let's look at one versus all, and the other one is all versus all. One versus all means this. Okay. Suppose you have 5 classes. How you do? Okay. Of course, you can say 5 classes, I take a class A. The remaining one, I can think all the remaining one is just like the other class. Okay. For example, if you take this web page, you say this one is the home page. Okay. And how I distinguish the home page? I just say all the remainings are non-home page. That means I actually change this multi-class classification into binary classification in that sense. Is every time I class this one, I take this one on the top. All the remaining ones, I don't care what they are all the remainings. It's another class. That means one versus all the others. Okay. Some people actually call one versus rest. Okay. Instead of one versus all, they use one versus rest. So that means you change this classifier. You get M classes. Okay. You change this one into one is any one, A sub 1. This is A sub remaining. Then how many classifiers you are going to construct? You are going to construct M classifier. You think about this. You have M classes, each one say, I'm now here, all the remaining is the remaining. Okay. So that means one versus all the rest. Okay. So that's one method. And how do you really judge a training data? Because you have M classifiers, okay, then you get a test data count. The subject count, which class it is. You ask this M classifier to vote, or to give you the weight, so give you the confidence. In that sense, you're doing some kind of ensemble or collective voting. But you probably know this one is not very powerful because the voting can say this one is not mine. Okay. But they don't know which one is. And maybe only one guy said this is mine. They took it. What about 2 guys said that these are mine? This is mine. It's very hard to judge because all the others say these are not mine. Okay. These 2 start competing, you actually cannot make a good judgment. So this is simpler, but it's less accurate because once the 2 classes start competing, you have a hard time to say it. Right? Then the second method is all versus all. Or you can say one versus one, where this goes. Okay. Suppose you have 5 classes. Okay. How do you get it? Then they do a little more, detailed work, a little more extra work. Means they actually try to construct every one. You try to check this. Okay. For example, you construct one classifier as A. We just do not say A, we just say C. Okay, C is a class. Say C1, C2, you get one classifier. That means we're competing between C1 and C2. Then competing with C1 and C3, C1 and C4, C1 and C5. Then after that, you say now I'll get into C2. And C2 will construct the classifier versus C3 versus C4 versus C5. You don't have to consider C2 versus C1 because C1 and C2, the classifier are already done, right? Then you get a C3, you say C3 versus C4, C3 versus C5. How many classifiers are you going to construct? You construct it. That's the exact number is m times m minus 1 divided by 2. Why divide by 2? Just because you don't have to say C1 versus C2, C2 versus C1, because they are just the same, right? So that's why you need to construct many binary classifiers. Like you think about it, you have 5 classes, you need to construct 10 classifiers because 5 times 4 divided by 2, you will construct 10 classifiers. Then how you really do the classification? You're still doing voting, doing some kind of ensemble. Okay. That means once you got this object came, say which class I'm in. Okay. Then everybody started trying to be, critical. Then if you get more people say C2, because C1, C2 says C2. Okay. C2, C3 says C2. Okay. You actually will be more confident because there are more people saying C2, it must be C2, right? So if you think about this one is a little more reliable because you get more votes, right? So that's a case, you say all versus all. It's a little more costly because you have to construct more classifiers, but it's a little more reliable as well because you get more people voting for you, you will be more confident my judgment is right. So that's basically the general philosophy. That's the 2 major methods. Of course, there are other methods, for example, hierarchy classifier. That means they modify your multi-class into hierarchies. Okay. You think about it even for ads. If you say, instead of there are 1,000 classes, try to say which ads you should put in. You may say, this one is for kids. This one is for aged people. You first do this classification, then they get kids. You say, this one is for girls. This one is for boys. Or this one is for toddlers. That probably is better. Instead of you get 1,000 different cases, try to compete. You do hierarchical multi-class classification. That also may work because you reduce the number of classes you have to handle at each time. Right? So there are cases like this. But usually we basically introduce this 1 versus 1, 1 versus all. Okay? And in practice, in many cases, you try to group the multi-class into hierarchies, try to reduce the number of classes you have to classify at one time. Okay? So you'll get a better classifier. So this is multi-class classification. Okay? In our homework, in our assignments, the program assignments, we do give you the multi-class classification as a programming practice. You probably can read this textbook once. In the meantime, you can go down to Wiki, go down anywhere. You can find more papers to read. But general philosophy, 1 versus all versus all, or some people using different terminology, that's the same. Okay. So any question on this? For this multi-class classification, there's another interesting one called error correction codes for multi-class classification. Error correction codes means actually sometimes you use one way to get a multi-class classification. But it may not be a very good way because there are so many classification methods or so many different parameters you can tune. You actually can work out many classifiers for this multi-class classification. And finally, you can ask them to vote. Okay. But sometimes the voting itself could be very tricky because Sometimes you may find that your case may get multiple people say yes. Okay. Then what happens? Whether you want to get is you get different opinions. Okay, some people say yes, some people say no. You want to make a position, say, I'm going to go to the yes side or going to the no side. Okay. Remember, every classifier may give you some error. Okay. Nobody can guarantee it's 100% right. Okay. Then this error correction code basically say, you try to see what is the one closest to you. That means look at the arrow, yes or no, you get all the differences. You will find which one is closest to you. Even somebody say yes, somebody say no. What is about, you think everybody get an arrow? But I try to make sure my distance is closest to some class. Majority people say yes or no, and I actually match this one the closest. Okay. What is the closest? Okay. Actually, this one is using Hamming distance. Anybody knows Hamming distance? Hamming distance basically say, if you say, suppose you have a code like this, 11111 or 10101 or something. If your case actually, suppose the other guy said 1111, you got 0000. This is the maximum distance because you get 7 classifiers, they all say 1, you all get 0, you're absolutely wrong. Okay. So that Hamming distance is the largest. What about, they say 1111, you get 11110. Okay. That Hamming distance is quite small. Of course, the closest one is they say 1111, you also say 1111. Everything is the same. The Hamming distance is 0. Okay. That means how many bits you are different from the others. That's a Hamming distance. Now we look at this case. We look at, I give you a simple case like this. You can see. Suppose you got a testing unknown, object. You want to do classification. Say, well, this one is in class C1 or in class C2, in class C3. And how do you judge it? Okay. You try to check which class is closest to your case. The Hamming distance is closest to you. Okay. So you probably can see, suppose you put X into all these classifiers. Then if you see the X, actually the distance to C1 is 5, to C2 is 3, to C3 is 3, to C4 is 1. Okay. That simply says, when you look at your case, you ask everybody vote, you try to check which distance, you finally may find C4 give you the shortest Hamming distance. Simply says you are closest to C4. It simply, if you think originally we say majority vote, now you do not look at it. It's similar to majority vote, but you check which one give you the shortest distance. Okay. You can see there are 1, 2, 3, 4. There are 7. I think it's 7 classifiers. 7 classifiers, they give you all the different votes. You see which one is closest. Okay. Then you find C4 is the closest to the thing you got. Okay. Then you will say now it is C4. Okay. So that's the basic philosophy of error correction code. That means none of them I trust 100%, but I see your vote, your 7 classifier vote. I just try to find which my case and your case, what is the closest one. Okay. So that's the error correction code. So this is another way to do multi-class classification. That means ask different classes to vote. That's when you get multiple class labels. Now, I give you another philosophy in classification called semi-supervised classification. What is semi-supervised? Okay. Semi-supervised means you give I give you lots of cases. But some cases, I actually clearly label them. Label them means I know this case is positive, this case is negative, I give the label. But there are lots of things I do not give the label. I also present it down there. Okay. That means semi-supervised means I got lots of cases. Some cases I label them. Okay, that means it's supervised. But some cases, there are many more cases I do not label them. Actually, that's not supervised. That's why we get a name as a semi-supervised. Semi means somebody's labeled, but some is not. Okay, not everything is labeled. I mean, not all the training data is labeled. Then you may wonder, you say, you give me so many, objects. Some labeled, some not labeled. What about I only use labeled? I just toss away those unlabeled. Actually, they give you unlabeled to some extent. It may help you instead of you just toss those unlabeled data away. You keep them. In your classification, they may be useful. They may be very useful. Okay. I just give you one example. I got one PhD student. He actually doing this semi-supervised classification in that way. He said, I only got a positive label. I could get no negative label, but I got lots of data. A typical application case could be this. You go to web. Okay. Suppose you want to find a professor's homepage. Okay, that's quite reasonable, right? You try to follow some professor, or you try to take courses from this professor. You want to find his or her homepage. That's very reasonable. But not everything is labeled. That means on the web, you get lots of data. Okay. Some, they label these are the professor's homepage. But the interesting thing is, nobody grab this data, say, this page is not professor's homepage. People are not bothered to label the others. They give you, for example, in computer science department, we have 70 professors. They put a label, say, 10 or 20 professors' homepage. There's hundreds of thousands of pages just in this department. Okay, you just go to the web, you can check it. Majority of people, they don't bother even to label it. Why I spend years to label those pages? Right? They don't label it. They only give you these partially labeled data. Okay. Then they grab a page, say whether this one is professor's homepage. They ask you to check. Okay. So that's the case. And how do you do it? You just toss away all those pages in your training. You actually have no negative label data, right? You can see that's a very rare case. That's the same case as this semi-supervised, but a little more radical because you don't even have any negative label data. So that's a case. Of course, while I talk this, I can introduce his method as well. Okay, that's a little radical, but it's still semi-supervised. Okay. Semi-supervised, there's one typical way called self-training. What is self-training? The self-training means this. Okay, you got a small label data set, positive and negative. Right? Okay, in that case, you can construct a classifier. Of course, because you ignore a majority other data sets, your classifier may not be of high quality because the training data is too small. Right? Training set is too small. But you construct one. That may help. How do you help it? Okay. You construct this classifier. This classifier has some power. That means the remaining data putting there, you will say, now I try to label those data. How I label it? Okay. Of course, there are lots of gray area. I cannot make a confident, resolution, confident decision. But I know, for example, grab this. This is professor's homepage. This one is not. What I do is I know this is so similar to this professor's homepage. This must be another professor, his or her homepage. I can confidently grab in and say, this is the professor's homepage. The other guy said, I look at these. These are not professor's homepage. But maybe this one is so similar to this. I'm pretty sure this one is not a professor's homepage. After this round, you grab more data into your camp, right? So say, these are professor's homepage, these are not. I get more, okay? Of course, I'm conservative because there are lots of gray area I don't want to touch. I want to touch something is really black and white. I know it because I constructed classifier. I'm very confident this one is black, this one is white, okay? Then actually you enhance your team, right? Because you get more data. You get more professors' homepage or homepage. You got this already. Okay, you get more. You get more, you become bolder. You say, now I construct another classifier. What I do? I construct another classifier. I actually get more other data. I can say it's black or white, right? You can see that. Then you can grab more. You can grab more. Until you got either you exhaust your cases or you get something really, really gray. I don't want to classify them. Okay. But you get a better classifier. I think originally you only have 1 or 2 cases. Now you enlarge your team substantially in a confident way, right? So that's self-training. That means those non-labor data, they are still useful to construct good classifier. Now I get into this PhD student, what he did. Okay. He actually did something similar. Remember, his case is a little more radical. Radical in the sense, he has no negative example. He only has professor's homepage. There's no negative example at all. But he still can do that. Why he can do that? He first look at the features. You think of a professor homepage may have something like a course taught or research area or something. Okay. Then you may find there are some pages that have nothing to do with it. Maybe it's just like a solution page or some ads page or put some kid's picture or something. You say these are, I'm pretty sure these are not professor's homepage, okay, based on the features. That means at the very beginning, you only have positive labor, you don't have negative labor. But you look at those already unlabored data, you just say, I'm pretty sure this guy is not a professor's homepage. Then you put into negative sets. Then you can start the game. You can see what he did is just modify it a little. You say, I have positive one. I try to look at all the features to create a very far remote negative ones. Okay. Then I'm bold enough, I start this whole 2-class classification in a semi-supervised way. And finally, I can get a very good result. And he did. He actually used SVM as his classification method. You can use any method. You can use Bayesian. You can use decision trees. Whatever method you want to use. The philosophy is just the same. Okay. Then another method to do this is co-training. What is co-training? Co-training basically say you got like at least 2 classifiers. Okay. 2 classifiers, you ask them to teach each other. How to teach it? Okay. That means you use 1 classifier, get a class label. Okay. For uninstant data, you get a confident the other one. You throw to the other classifier, say you do it. Okay. You do it, at least I partially trust you. Okay. Then this classifier returns something back. Say, now I did more things, you do the remaining. They start going back and forth. You get 2 classifiers, they mutually enhance each other. Okay. So that's basically the co-training. So yes? Okay. Yeah, the question is whether you think the other classifier is better, why you want to use 2, not use 1. Actually, this is similar to ensemble. You think about ensemble, we said you get a voting, you get multiple doctors. Okay, even each doctor is bad, but you get multiple doctors. As long as they do good thing, usually you get joint vote, you will be the winner. Okay, so that's a similar philosophy. That means you may not completely trust each one, but you can assume each one doing something overall better than mess it up. Okay, so that means you trust each classifier at least have higher than random guess. It's a little over than 50 if you get a 2 classifier. You say a little over than 50% the random guess. Because you throw a dime, you actually can see the face. The random guess is purely 50-50, right? But now you say this classifier, at least they make mistakes, they're better than 50-50. You get something. Then you actually this co-training is like both sides guard each other, okay, and help each other as well. So that's a general philosophy. Okay. So the co-training is also popular, but the first one, the self-training actually is very popular use. If you go down to semi-supervised classification, majority of people just use one classifier, still can do good things. For those unlabeled data, they want to use them. Okay. So this is the semi-supervised. Another popularly used method called active learning. What is active learning? Active learning means that you assume people give you label. Every label will cost something. Okay? It's not free. You just think about it. You go down to experts. For example, you want to ask those tissues, cancer or non-cancer. You must go down to some good expert. The expert will ask you to pay for it. Think about this. They may say, I do 10 labels, you have to pay me some dollars, right? But you have a limited budget. Of course, you want to get more training data, but you have a limited budget. The problem becomes which tissue, which object you want to show to this doctor, get a label which may help you. Okay. You don't want to say, it's more like this. Suppose you got a SAT test or some kind of test, like you prepare for CS412 final exam. Okay. You know this guy got an A+. You want to ask this guy. But this guy said, you have to pay me, okay? Or something, I don't have time. You have to at least buy me lunch. Then the case becomes, which question you want to ask? Of course, you will say, I will select a good question to ask. If this one I'm clearly no, yes or no, why I have to ask this expert? Right? I only ask something I think is more difficult, it's tricky. I do not know the answer. I will go down there to ask the expert. Okay. That's a common case. This active learning actually plays the same role. That means you may have expert or human labor, or you can say oracle. Oracle means you go down, somebody will tell you what is right, what is wrong. This kind of oracle. That means any expert give you the label is costly. You have to select what instance to go down there to ask for label. Okay. So that becomes one called pool-based approach. Is use a pool of unlabeled data. That means you got this unlabeled data, it's a pool. You try to select it, carefully select which question you want to ask. Then you go down there, one label may worth a lot. Okay. So that means you use minimum number of label data or questions to get a maximum benefit. That's the philosophy of active learning. Of course, you probably want to see there are lots of tricks. For example, if this label you ask, you can solve a bunch of problems, you can solve most of the problems, you may pick up this label. Or this is very difficult, or this is very gray. Okay, there are many, many different ways to thinking about which question you should pose. Okay. And usually they say how to judge an active learner is minimum cost, maximum benefit. That's a general philosophy. So they may give you called the learning curves. Learning curve simply says, you give me the label, my learning curve is sharpest. That means I can learn most. I'll ask you on this, I probably get some benefit. Okay. So this is the active learning. Active learning also can be used for any classifier. Like a deep learning, you may get an active learning mode. And you get a probabilistic graphic model, you also can get an active learning mode. Active learning is just a philosophy to help you to get a minimum cost to get maximum benefit. Of course, there are still lots of research issues. You can work on. This is still active research area. Means how people can work out the best active learning strategy and which one you should raise. Another one called transfer learning. Transfer learning basically say, you work on this domain, you learn something. Then you go down to another domain, try to learn something, it may help you. Actually, the transfer learning in our typical studies, you also find it's very useful. For example, if you learn well on math, probably you go to computer science, certain courses, you see that benefits a lot. So there's many things similar. Even I never seen it, but I learned the methodology. I can handle it. By learning math, actually helped me learning computer science, or even helped me learning music. Okay. So to that extent, transfer learning in reality, it is popularly used. But the problem is some are very close. For example, you learn math, you say, help me learning some courses in computer science, it is quite right. But if you say learning math, help me learning sports or music, it may or may not be quite true because this field probably too separated. That transfer learning may not help you that much. So that also the same thing as transfer learning. Transfer learning means you can learn, you can see. You get a learning system, learn different things. Okay. Then you probably want to say the transfer learning philosophy is you learn 2 or 3 different fields, then you try to get into another, the third field. Okay. So then whether you can transfer your model to the third field. In most cases, the knowledge is not so easy to be transferred. You still need a learning process. Okay. So that transfer learning, the general philosophy is how do you pass your structures or something down to the others. One typical advice is if you learn 2 fields, you want to solve the third one. You want these 2 fields to be separate enough. Okay. It simply says these 2 are not just repeating, duplicating. You still just learn 1 field. And also you want these 2 somehow similar to the third one. Okay. So you want to see the complementary of these 2 can help you to learn the third one. Okay. So that's the philosophy of transfer learning. The transfer learning, the general philosophy is you try to build a model based on the new data, which is different. Sometimes it's not rather different from the previous. Okay. One way could be you learn, for example, for one company, you want to help another company. The company should have some similar nature. Or you want to learn yesterday's thing to help you today. Yesterday and today also should share some kind of similarity. That means you want to see how similar you can do this transfer. There are still many transfer learning methods, but there's one I'm going to introduce you called transfer learning ADA boost. We already know the ADA boost. Okay. The transfer learning ADA boost, the general philosophy is now you have 2 kinds of data. You have the original source, and you have a target, but they are in different domains. They have different sets. Okay. Then what you do is you try to, based on the original model, originally seen learned in the, which is the source data, the original source, classifier. For example, you say this part is math. Okay. Then get into the new one. Suppose this part is computer science. What you do is you try to use this model to predict the computer science one. Sometimes you are right, sometimes you are wrong. Right? That's obvious. And if you did it wrong, remember the ADA boost said anytime you did it wrong, you put more weights on this new data, you go back again, you retrain it. This transfer learning has a similar philosophy is you reweight the misclassified sources. That means, for example, you use the previous one, you try to classify it, you find, oh, this time it's wrong. What you do is you go back and reweight it. But reweight it because you do not have sufficient labor here. You reweight your original source. That means you say, why I got it wrong? Because in math, they do it this way. Now in computer science, I have to do a new way. Okay, this way was not very effective. I lower down the weight. That means anytime the original source, I know actually it's wrong, it's not effective. I can lower down the misclassify the original source. I redo this training than I use in the new data. You first see. It's a little different philosophy, but philosophically it's the same as AWS. But how do you weight it is different. Because in AWS, it's anytime you go wrong, you actually put more weights. The next round you retrain it, you'll get better. Because you are dealing with the same data. So this transfer learning, you deal with source and target, you find this source is not effective as this. You modify your source. Okay. You're thinking about it. Suppose you get a legal system. Originally it was British, now it's American. You will find that something is effective, you use it. Something not effective, you say, I have to lower down this weights on the British law code or somehow. Then I retrain it, I use it, maybe more effective. Okay, so that's the typical case. So this is the transfer learning. It's also popularly used in practice. Okay. So now we finish all the classification introduction. I should say this classification introduction I did here, comparing to machine learning course, I mainly doing a little like high-level overview. Because of the data mining course, we only got like 2 or 3 weeks to handle this classification instead of in most machine learning course, they got the whole semester to handle it. So a lot of very critical methods I only introduced in the idea level, philosophical level. That means if you really want to go deep into this, you should take dedicated courses. For example, I do not know whether we have a deep learning course on campus. If you're really interested in deep learning, not count. No, I teach you something because I teach you something just the philosophical ideas on these deep layered neural networks. The detailed mathematical problem, all the different like long, short memory, there are so many different deep learning models. You should go down there to study it instead of thinking I teach you everything. Okay, I teach you, so shallow, so high level. It may not be that applicable. Okay. But at least you get general ideas. Okay. So there are lots of books. There are new books as well. For example, the deep learning, a good new textbook they claim is published in mid-November. I already booked it. I haven't received it yet. I do not know whether they will delay or not. But anyway, there are lots of good books here I introduced. For example, one interesting book is Bishop's Neural Network for Pattern Recognition. And Bishop got another very good book on machine learning, on pattern recognition and machine learning. It's published in 2005 or 2007, I forgot. I do not know. I should put that one as a textbook here as well. But anyway, there are quite a few very good tutorials books you may like to read. Okay. This one essentially is I only put one link. That's a new paper, TP class. I put a link, you click, you can download the paper. All the remaining ones are the classical ones. It's in the textbook. Okay, so now I finished this one. This is where it is. Anybody can judge? Yeah, it's still Chicago, right? You look at the water, you think whether it's New York, actually it's Chicago. In New York, the river is much broader, right? So this one is pretty narrow. That's a downtown Chicago in the, I think it's a Myers High or someplace. Right. I do have several other slides because they are useful. I still do not want to delete it, but they're not covering the class. Simply it's not covering the exam as well. But you should know there are still many other. For example, the regression tree. There are lots of model tree. For regression, they are still popular use, but we deal with classification are not handled. Okay. Now we have a few minutes. I give you a very short introduction on the very last chapter, which is clustering. Okay. Actually, for this chapter, I should say is in my Coursera course. That means if you want to go to cluster analysis, Coursera, I think it's still ongoing. I do not know it's free. You can watch the video. or you have to pay something. Maybe it should be free. That's what I thought. But anyway, if you probably will not be able to do homework exercise. That one will register, pay, I think you pay $49 or something. But the video probably should be free. I actually try to coerce the new one exactly the same as the Coursera one. That means actually this slides, the whole set of slides is equivalent. Even this one, if I got scared. Even this one is only one chapter in our lecture. In Coursera, it's one whole course. Okay, that means it's exactly the same set of slides I'm using for the whole Coursera. But it's not like last year's Coursera. Last year's Coursera, I actually have almost double the material. And the students complained. The students said it's just too much stuff to learn. So then, remember in this textbook, I have 2 chapters on clustering. One is this one is the other chapter. That previous last year's Coursera course, I covered both chapters, a little more than that. This year, I try to be conservative. I cut it by half. Then you see, it only cover this chapter. Okay. But there, I say it's 4 weeks. Okay. Here, we probably will have less than 4 weeks. Okay. That implies you have to learn more. But I will see, because in the very last lecture, evaluation of clustering, I said the coverage will be based on the available time. That means if we do not have enough time, I may only cover 1 or 2 methods. The remaining one is just your reading. If you're interested, you can watch Coursera. Otherwise, we're not covering any exam or homework. Okay. That means I give you only very, very important ones. The remaining ones is your reading part. Okay. So cluster analysis philosophically said unsupervised learning. That means previously I discussed all these, I give you labels. That means we have supervision. We have an expert. Even expert learning said the expert is very expensive, but you still ask them to give you a label. But clustering means I don't ask anybody to give me a label. I just based on the data and their properties, their features, I try to group them into different groups. Okay, that's the philosophy of clustering. So in the next lecture, I'm going to discuss systematically on the cluster analysis. Thank you.